come back to what we were doing over here. Okay? So this here is a nice quadratic equation, a nice parabola. Okay? What if I wanted to find out what type of stationary point that was? Okay? So type of stationary point, there's two which we'll look at. There is actually a third, which I'll highlight as well. It can either be a maximum, or it could be a minimum. So just by looking at the graph, what type of stationary point does this look like? Why is it a minimum? It's the lowest point which is local to that set of points. So if I just zoom in on that bit of the graph, are you happy that's the lowest point of the graph? The graph doesn't drop below that point. Okay? Whereas if I come back to the cubic graph which I had, this one here, okay, two stationary points, one there, what would that one be? Yeah, what would that one be? Okay. You happy? But is it true, is it a true maximum, and is this a true minimum? Because if it was a true maximum, say, it means that that is the highest possible point on the graph. Is that true?
There's other points above it.
Exactly, the graph keeps on growing on that side. So it's not true to say that that point is a global maximum. Okay? So global means that it's true everywhere. So if it's a global maximum, it means it's the highest point on the graph, like over the entire graph. Okay? Or if it's a global minimum, like this one would be, it means it's the lowest point on the graph ever. Yeah? Would you be happy this would be a global minimum? Because everywhere on the graph would be above it. Okay? So it's true to be the lowest point on the graph across the entire set of points. Okay? Whereas this one here is not a global maximum, we call it a local maximum. Okay? So global means it's true everywhere. Local means that it's true for that particular region. So kind of from here to here, it is true that that would be a local maximum. Okay? But as soon as you get over here, there's points above it. You don't need to explicitly say global maximum or global minimum, or local maximum or local minimum, but I think it's worthwhile being aware of it. Okay? Likewise, with the same thing here, this would be a local. This would be a local minimum. Okay? So if I say in sort of passing, global versus local, this is just literally what I mean. Global means it's true everywhere for every set of points. Local means it's just true for that particular region there. Okay? All right, fine. So I wanted to establish from my stationary points business, is it a maximum or is it a minimum? Let's think. So let's go back to this graph here. Now I said my gradient is just simply like my roller coaster. Okay, so over here I'm really facing downhill, it's really negative. As I move closer to the stationary point, I'm getting less negative. Would you be happy with that? Yeah, so here I'm really negative, really steep downwards. Here I'm slightly less steep downwards. And here I'm kind of flattish. Yeah? But I'm still downwards. So I'm still negative, everywhere on the left I'm still negative, but it's just I'm getting less negative. Does that make sense? So it's still negative on the left, but it's just less negative. And in fact, as I move over here, would you say I'm getting more positive? Okay? So this point here, let me draw it out, is a minimum, okay? And what happens as I move from left to right, so as I move from left to right, I am getting less negative. Or another way of saying that is that I am getting more positive. Does that make sense? So I'm getting less negative.
It's getting bigger, so it is more positive.
Okay? So another way which I can establish this is that my gradient, or the rate of change of my gradient, is getting more positive. In other words, it's getting bigger. Okay? So my gradient, so dy by dx, that's my gradient, is getting bigger. pause for a second. Does that make sense? Does that make sense?
Yeah, it is increasing all the way.
Exactly.
If you start from the left.
Exactly. So I can literally just say, this kind of establish it down, use a really big word there. It's increasing. Okay? Over here, just to establish, over here I'm really negative, then I'm slightly less negative, then I'm not very negative, then I'm positive, then a little bit positive, more positive, and then really, really positive. So in other words, I'm increasing, my gradient is increasing. Okay? So my gradient, dy by dx, is getting bigger. Okay? Well, if I say it's getting bigger, it means it's getting more positive. Okay? More positive. So in other words, dy by dx, okay, is getting bigger and bigger and bigger and bigger. So I'm saying the rate of change of my gradient is increasing. Okay? Now are you happy? All this notation here means it is just rate of change. Yeah? This d by dx business is just differentiation. Just differentiation. Okay? In this case, I'm just talking about gradient. In this case, I'm talking about the rate of change of my gradient. Okay? If I do a little bit of algebra with this, would you be happy that I'd end up with, well, d squared y on the top, or I'd say d2y on the top, and on the denominator I end up with dx squared. Well, rather than writing dx all squared, I'm just going to be a little bit lazy with my notation and just write that. Okay? So what this literally means is that at a minimum, d2y by dx squared, notice how I say that, d2y by dx squared is getting bigger, it's increasing. Yeah? Now this d2y by dx squared business just means take your derivative, wherever it is, it's gone, take your derivative and then differentiate it again. So it's the second derivative. You just differentiated your function twice. Does that make sense to everyone?
Yeah.
Yeah? What do you think it's going to be for a maximum? So if I draw a maximum on, could be local, could be global, doesn't matter. There's a maximum. Okay? Would you be happy now as I move from left to right? So I move from left to right. What's happening to my gradient?
Decreasing.
It's decreasing. Yeah. So I move from left to right, it's getting more negative or less positive, doesn't matter which way you look at it. Which is absolutely right, I suppose. Basically sums up to be decreasing. So my gradient is getting smaller. Okay? So dy by dx. Which literally means, if I was thinking about it in terms of this, the rate of change of my gradient. Rate of change of my gradient must be getting smaller. So in other words, it's less than 0. Okay? So the rate of change of my gradient, that's literally what that says, rate of change of my gradient, is getting smaller. Okay? Let's see it in action. I think an example will make things a little bit clearer. This is a really fundamental idea. Okay, it can either be a maximum or a minimum. Okay, but the point is, if you just know information about this, the second derivative, once you differentiate a function twice, if it comes out as positive, it means it must be a minimum. It must be a minimum because your function is increasing. If this comes out as negative, it must be a maximum because it means your function is decreasing. Okay, let's have a look.